Today we're going to take a look at logarithms, okay? So what a logarithm is it is an operation, much like adding, subtracting, multiplying, squaring, square rooting. It's a mathematical operation that you're not particularly familiar with, okay? And it is the inverse operation of raising something to an unknown power. So let's talk about that for just a second, right? We've looked at problems before where we've had something like x to the second power, and we've talked about how you would undo this, right? The inverse operation, right? So here's our operation, squaring something. The inverse operation of that would be taking the square root, right? Or if we had x to the fifth power, we would take the fifth root. So we have that, and these two things are connected because whatever your power is here, that's the index root that you need to take to undo it. So the problem comes into play that now we're looking at problems like 5 to the x. So when I go to do my inverse operation, even though it's an exponent, I run into a problem because I don't know what to use for my index number, right? So I can't just take a root to undo this because we're going to run into this issue, okay? So what we're going to do instead is this is where, instead of using this is where a logarithm comes into play. We abbreviate it log most commonly, but that's what it is. So a logarithm is an inverse operation of raising something to the unknown power. So you would take the log of this to get back to whatever x is. Okay, so that's kind of what we are talking about. Now, first of all, we need to take a look at the general format of what a logarithm looks like. So let's use as an example a pretty easy statement. So 3 squared equals 9. We all agree that that's true. This is what we would call exponential form, okay, because it's got an exponent in it. Logarithmic form. And what this expression would look like in logarithmic form is it looks like this. So it's log, that's the abbreviation, and then it's a subscript 3. So much like how an exponent is a little number written slightly offset to the top, this is a little number written slightly offset to the bottom. And you can kind of see if you look down here, sort of what those are going to look like. Okay, so it would be log base 3 of 9 equals 2. Okay, because again, the goal of the logarithm is to figure out what is this number, right? So you take this logarithm and it gets you that number back. So this is logarithmic form. All right, now talking about this guy, how you would read this. So the way that you say this in math is you would say it's the log base 3. So the little number down here is your base. That comes from the fact that in exponential form, right, that's the base number on the exponent. So we say it's a log base 3 of 9. That's how you'd read that. Okay, so log base 3 of 9. This is a log base 2 of 1/4. This one's a log base 4 of 8. Okay, so that's how you'd read those. Okay, so what we're going to work on first is being able to switch between exponential form and logarithmic form. Okay, because having that skill of switching forms is super, 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 super helpful as you're trying to evaluate these. Okay, so basically, you need to find a way that you can remember the pattern to flip from one to the other. Now, different ways work for different people. Some people sort of look at it like a shuffling, a reordering of things where they're kind of like, you know, swapping these two numbers almost. Like, you got to figure out what works best for your brain to help you remember that. A really stupid story that I made up when I was your age and I was using logarithms for the first time, and I had to remember this. And for whatever reason, this stupid story that I made up for myself, right, is something that has stuck with me for, you know, years since then, right, where I still use this when I go to transform logs. Okay, so it's dumb. I'm telling you, it's a dumb story, but I'm going to tell you anyway. Okay, so this is a story about a family. They're a very unhappy family, and they live in a log cabin, right? Log cabin, you see what I did there? Okay, so it's a very unhappy family. Everybody in this family is unhappy, and they just wish that they could be someone that they're not, right? So the little number, the 3, the base number, right? So the little number, he is just tired of being the littlest number all the time. He's always getting picked on by his older brothers, right? So all that he wants in the world is to become a big number. So my little number here becomes a big full-size number. Okay? The number in the middle is sick of being in the middle. If you've ever had to sit in the back seat in the middle with your feet on the hump for a long car ride, right, you know that being stuck in the middle is not a good time. So the number in the middle, he just wants to be left the heck alone, right? So he just wants to go over and be by himself on the other side of the equation. Okay, and then the 2 on the outside here, he's lonely because he's by himself all the time and he really wants to have a friend. So he doesn't really care. Okay, so that's my stupid story. It doesn't really have a happy ending. They're all just unhappy, right? So my unhappy family that lives in a log cabin, the little number becomes a big number, right? The number on the outside wants a friend, and the number in the middle wants to be left alone. Okay, and stupidly, that is a story that I tell myself whenever I need to change form. So that's what we're going to practice in these 2 sections, is just changing forms. So let's take a look at this guy right here. So rewriting this, I'm starting in my log cabin. Okay, so the little number wants to become a big number. So I'm going to have a 4. Okay, the number on the outside is lonely and wants a friend. So that's going to be my exponent. Sorry, I just have to stop and yell at a cat for jumping up on my counters and eating food off of the counters. So I'm sorry, I lost my flow. I'm going to have to start over. Okay, so the little number wanted to be a big number, right? The number on the outside wanted a friend, right? And he's willing to do whatever he needs to have a friend, even if he has to be a little number. Okay, and then the number in the middle, the 8, just wants to be left alone. So he goes on the outside by himself. Okay, this guy right here, right? The little number wants to become a big number. The number on the outside wants a friend. And then the number in the middle wants to be left alone. And you can look at that and say, oh yeah, that's true, right? 2 to the 4th power is 16. Okay, and this last one, so the little number wants to become a big number. Number on the outside wants a friend. Number in the middle wants to be left alone. And again, you can look at that and verify that, yeah, that's true. Okay, so you're going to need to be able to switch these forms. All right, and just a warning for you, I don't want you to look at this and say, oh, well, I can figure this out just by looking at it and say, okay, well, 2 to the 4th is 16, right? Because sometimes I will give them to you where they're all letters and you have to rearrange them. So you're going to need to know the pattern, not just how to use the numbers to make an expression. Okay, so now let's look at these ones. These ones, we're going to go the opposite direction. So for these 3, we're starting here and we're switching into logarithmic form, okay? So when I do these, I literally, so in my little log cabin, the little number wanted to become a big number. Well, that was the 5. Okay, the number that was in the middle wanted to be left alone. So that was the 125. And then on the number on the outside wanted a friend. So that was the 3. Okay, this guy, so my log cabin, the little number wanted to become a big number. So that's the 8. The number in the middle wanted to be left alone. So that's the 4. And the number on the outside wanted the friend. So that's the 2/3. Okay, little number wanted to become a big number. The number in the middle wanted to be left alone. And the number on the outside wanted a friend. And there we go. Watson barking in the background, as usual. Is I'm going to basically pretend that this equals X and then convert it, right? So the little number becomes a big number. The number on the outside, that's my X, right, wants a friend, and the number in the middle wants to be left alone. And then it's pretty easy to look at that and say, okay, well, 3 to what power is 81? Well, 3 to the 4th power. Okay, so that expression, log base 3 of 81, that equals 4. Okay? All right, this guy here, so again, I'm sort of pretending that this equals X, and then I'm converting it. So little number becomes a big number. Number on the outside wants a friend. Number in the middle wants to be left alone. So 49 to what power equals 7? Well, we'd have to square root it, right? So the 1/2 power. Okay, this one, we want to know 2 to what power equals 64. So that would be 6. Okay, this guy over here, right? Little number becomes a big number. The number on the outside wants a friend. The number in the middle wants to be left alone. So 25 to what power equals 125? Okay, well, this one's a little bit tricky because 25 squared would be like 625. That's way too big, right? So how do we get from 25 to 125? Well, we'd have to start with the 25. If we square root it, that gives us 5. And then if we take that and raise it to the 3rd power, that would get us 125, right? So power over root, it would be 3 over 2, right? So 3 over 2 is what that would simplify to. Okay, this guy, we want to know 2 to what power equals 1/8, right? Little number becomes a big number. The number on the outside, that's our imaginary x, wants a friend. And the number in the middle wants to be left alone. So to go from 2 to 1/8, I would have to raise that to the 3rd power to go from 2 to 8. And then flip 3 to get from 2 to 8, and a negative to flip it to 1/8. And there we go. Okay, this one, we're doing 1/2 to what power equals 8. Okay, well, to go from 1/2 to 8, I'm going to want to flip this to make it into a 2, right? So it's going to be something negative to make it a whole number. So if I flip it, that'll make it a 2, and then 2 to what power gets me to 8? Well, 3. So that's going to be -3. Okay, this number, little number becomes a big number. Number on the outside wants a friend. Stuff in the middle wants to be left alone. How do you go from the square root of 6 to 6? You square it, right? So you multiply it by itself. Okay. Next one, we want to know what number, or 2 to what power equals 1/4. So I'm going to have to Cool, we're getting there. All right. So down here, this is where we're going to start hitting some of the special cases when we're looking at these. So let's take a look at this guy. So this one, we want to know 15 to what power equals 15, right? Well, 1. Okay. So thing that you should notice here, right? Think about it. No matter what this number was, as long as these two numbers are the same, it's always going to be kind of set up like this, right? So anytime these two numbers are the same, your log is always going to simplify to just 1. Okay, that is going to be an important thing to know, that if you're taking a log base the same thing, then it's going to be 1. All right, next one, log base 7 of 1. So again, converting it, little number becomes a big number. The thing on the outside, our imaginary x, becomes wanted a friend, and then the stuff in the middle wanted to be left alone. So 7 to what power equals 1? 7 to the 0 power equals 1. Okay, again, think about this one, right? No matter what this 7 was, if your answer is 1, it's always going to have to be 0, right? Because any number to the 0 power is what gets you 1. So anytime you have a log where the argument here is a 1, you're always going to have an answer of 0. So log base 100 of 1 is 0. Log base 8,000 of 1 is 0. Okay. All right. This guy here, log base 10 of 1. So when we convert that, it would be 10 to what power equals 1? Well, 0, right? 10 to what power equals 1? Well, 10 to the 0 power equals 1, right? So there's another example. As long as your argument's a 1, it's going to work out that way. All right, now these guys, let's take a look at some ones where we have bases that are square roots. So this one, I want to know square root of 5 raised to what power equals 5? Well, I'd have to square it to get rid of the square root, right? So I need 2 square roots of 5 to get up to a whole number 5. Okay, so that one wasn't too bad. Now this one's going to be a little bit more annoying, right? So square root of 5 to what power gives you 5 times the square root of 5? Okay, well, we already established that you need 2 to get a 5, right? So I need 2 square roots of 5 to get this guy. And then there's also one additional square root of 5, right? So altogether, that's 3 square roots of 5. Okay, so again, thinking about it a different way, right? 5 times the square root of 5. This guy, I could break into the square root of 5 times the square root of 5, right? And this is just still itself. So it took me 3 square roots of 5 to be the same thing. All right, this guy, so we want to know square root of 5 to what power equals 25? Okay, well, 25 is 2 regular 5s. And we know that we need 2 square roots of 5 to make up 1 regular 5. So that's going to be a total of 4 regular 5s. Okay, so 25, right? You could break that into 5 times 5. And we want to know how many square roots of 5 does this make up? Well, this would be 2 square roots. So the first thing that you kind of want to do with these to make your life easier is rewrite that as a fraction, right? So I'm going to rewrite that. That is 1, this would be tenths, hundredths, thousandths, 10,000ths, right? So that's 1 over 10,000. Okay, and that's going to be helpful because now what I'm looking for is I want to know 10 to what power gets you 1 over 10,000. Okay, well, I know it's going to have to be a negative exponent to flip it, make it end up in the bottom, right? And then the question is just how many tens does it take to get up to 10,000, right? 2 tens gets you to 100, 3 tens would get you, sorry, 2 tens get you to 100, 3 tens would get you to 1,000, so 4 tens is going to get you to 10,000. There we go. Okay, this guy, we got our friendly number e showing up here, right? So our friendly number e, okay, if I convert this, we want to know e to what power equals e to the 4th, right? Because this guy, that goes together, right? So think of it that way. It's this number to what power equals that. And then you can kind of look at that and clearly see, oh, look, it's 4, right? So 4 would be our answer to that one. Okay, so really quick comparison. Remember back here we looked at this one and we said that if these numbers are the same, it works out to 1. Well, here we've got where these ones are the same, right? And it works out to be just whatever your exponent is. So kind of what happens is that these guys cancel to 1. So the log base e of e canceled to 1, and then 1 times 4 is 4. That's kind of how I think about it. All right, and then this last one, we want to know 2 to what power equals negative 4? Well, 2 squared would be 4, but to get to the negative, that's not possible, right? Because a negative exponent would make it flip, not make it a negative number. So this has no real solution, okay? So at any time you take a number, your base number, you raise it to an exponent, right? It can't be negative. If you have a negative argument in your log, that's your cue that there's no real solution to that problem. All right, now 2 things to make note of down here. There are 2 special logs that have special kind of symbols / buttons. Okay, so the common log is when you have a log with a base number of 10. Okay, so instead of writing log base 10 of x, all that we would write is just log of x. Okay, so just like how in a square root the 2 is assumed, right? In a log, if there's no number there, you assume it's a 10. Okay, and that's based on the fact that we have a base 10 number system. Okay, but then similarly, a log base e is also a special log. okay? This one is called the natural log. So remember how we said when we were looking at E, we mentioned how it's called the natural base, right? This is the connection. It's called the natural log when E is the base number, okay? And you write that as ln of x, okay? So it stands for natural log, but it's kind of like log natural because it's Latin, right? So it's sort of backwards and not quite the words log or natural, but close enough, okay? So when you go to do those on your calculator, right, there's a button here for a log and a button here for an ln. Okay, so by default, a logarithm is just an operation. Okay, it's an inverse operation, just like how subtraction is the inverse operation of addition and division is the inverse operation of multiplication. This is the inverse operation of raising a number to excuse me, an unknown exponent.